our last colloquium of the year, and we're ending strong. It's my pleasure to welcome you, Dr. Veeshan Narinesingh. I asked her how to say that correctly. A little bit about V. I actually met V for the first time virtually during a blocking workshop that was held virtually in 2021. We chatted a bit, even though it was kind of the virtual environment at the time. I remember being surprised that you were a student at the time, because V is never afraid to ask questions and join in the discussion. And it was great to get to meet you then. And it's a pleasure to have you now. So a little bit about V. He got his PhD in physics in 2022 from the City University of New York, where he worked with Jamie Booth, using a hierarchy of models to examine links between blocking the general circulation and extreme events. From there, he went on to do a postdoc at Princeton and GFDL Cooperative Institute for modeling in the Earth system. And he is a GFDL now, where he's a federal physical scientist, and he continues to use models to better understand the large-scale circulation and its links to extreme weather. In parallel to all of his research, he is also a very strong advocate for diversity, equity, inclusion, and accessibility in the sciences. He's done a lot of great work with that. He's even, I think you're like the director of community outreach at the Harlem Gallery of Science. You even founded a company, which is Scientist Academics, which works on academic mentorship and program consulting, if that's correct. And all of that is strongly linked to his DEIA work. And you'll talk a little bit about the DEIA work within this talk. So without further ado, V, I'll let you take over.
Thank you. Can you hear me okay? All right. Listen, I was getting a little nervous coming here, but after meeting all you nice people today, I feel like I'm amongst friends. So thanks again for having me. I met Stephanie when I was doing my PhD, and I was like, wow, this thing is really cool, really nice. And she was very encouraging, and I think maybe in some way helped me become the scientist I am today. So thank you, Stephanie. Thank you for the opportunity. And thank you all for all your hospitality today. I've been to a bunch of these kinds of visits, and I must say, this has been the nicest and coolest and warmest department that I've ever been in. So shout out to all of you guys. So how you all doing? You doing all right? Having a nice time? Oh, yeah. All right, very good. I know we got some Boricuas in the room. What about Boricuas? Yeah. I got my Puerto Rico shirt on. My wife is Puerto Rican, so I got to shout out. Okay. All right. Listen. Today is maybe your lucky day or your unlucky day, depending on how you want to think about it. You came here for one talk, but you're going to get two. And that means I'm going to go through it really quickly, and I'm sorry, but hopefully some of it sticks. So again, my name is Veeshan Narinesingh, and let's just jump into it. So I start off with this because I feel like as scientists, it's very important to share our identity. Our identity shapes who we are, motivates what we do. It expresses our cultural lenses, so on and so forth. And I can take it way back, starting with my grandmother here. This is my grandmother. Her name was Dora Bridge Mohan. And she started off as a cane cutter in the Caribbean island of Trinidad. And she used to cut cane, and her parents were indentured servants all over there. And she worked for $14 every 2 weeks. But somehow, I don't know how, she never graduated high school, but she became the first woman senator in Trinidad ever, which is kind of crazy. And the thing about her, I don't know if you know Caribbean women, but they're spicy. And she didn't take anyone's crap, that's for sure. And she really fought for workers' rights. And I feel like that has invigorated me into what I do these days. So, I don't know, somehow or the other, she saved her coins. She went with my mom, my dad, my uncles, my aunties, some of my cousins, them. And they decided to move to the Bronx for some reason, where I was born. And I'll tell you, the Bronx is kind of crazy. But we lived there for a while. It's pretty And then here's my mom too. And my mom is another amazing person. I remember I was growing up, I wouldn't really see her a lot though, because she'd always be at work. And I would say, if your professors think you got it hard and you do a lot of work, you're not touching my mom. This lady double shift every day, overtime every week. So definitely they invigorate me anytime I feel like, I'm not doing enough or whatever. I just think back to all the sacrifice and struggle, and I let them invigorate me, the spirits of my ancestors. So eventually, my mom, she wanted to get us out of the craziness of the city, and she moved us upstate to the suburbs of New York. And I went to middle school and high school in Middletown, New York. Very beautiful place, as you can see. But me, I was more interested in my friends and hanging out with them. So when I turned 18, she kicked me out. She said, "You gotta go back to the Bronx and live with your sister and go to school." She said, "All you're doing is studying, friend. You're not studying any book, so you go back with your sister." So she sent me, and I was a very bad student, as you can see. I failed physics the first time I took it, and now I got a whole PhD in it. So, it was crazy at first. But then, when I was going to city college, there was all these great people around me that really helped motivate me. I saw a lot of classmates that came from a similar kind of immigrant background as me, and it helped me realize that I can do great things in this world. So that's what I tried to do. Ended up working in a lab doing condensed matter optics with quantum dot solar cells, and that was pretty dope. And I was like, maybe I am smart enough to do a PhD. So I decided to do a PhD in physics because I wanted people to think that I was smart. There's a picture of me and my boy Mandeep, and he is like, "Dude, how do you not know this? I learned this in high school." And I felt pretty dumb, but I got through it. And originally, I wanted to be an astrophysicist, but because I was in a physics program, so I went and I emailed every single astrophysics person, and they either didn't answer me or they were like, "Sorry, bud, I can't take you." So I was like, "All right, I guess I'll do the next best thing. I'm gonna learn some coding. That way, I could work at Google and become really rich or something." So that's what I did. And there was this opportunity with NOAA where they were providing minority fellowships. I think Myra was in a similar kind of program as well. And this changed my life because then that's how I pretty much accidentally became a climate scientist. So in this program, it was really good. It connected me with GFDL. I started off as an intern there. They were really nice to me. And I was like, what, maybe I'll just do this as my career. So I'm a thread there. So that's my story. I hope you liked it. And then let's talk about what we're going to talk about today. So there's my introduction. First, we're going to do some hardcore climate science stuff, I guess. Some weather extremes related to heat extremes stuff, atmosphere blocking. And I had an incident last week where I experienced some racism in the climate science field. And I was going to take this part out because I felt very demoralized. Like, people don't give a crap about this. A lot of people don't. So maybe you guys don't want to hear it. But then I thought to myself, okay, I'm going to hear it anyway. Because this is what we're talking about. So this is what we're here. We're doing it, yeah. But you all seem pretty great and seem to care about this, and I respect that. So let's start with this part. Heat extremes, we know they're really bad. So obviously they pose all kinds of risks. Human health, ecosystems, infrastructure, and then ultimately the economy of all that you care about. But the physics of them is not something that's well understood. And this is due to a lot of different things. So I said, okay, maybe I should study heat extremes. So that's what I did, and I'm going to talk to you a little bit about some work I began last summer with an intern. Her name is Berenice, and she just got accepted as a presidential fellow at Boston College. So shout out to her. Maybe she's listening. Can you clap for her if she's listening? Very proud of her. So we did this work, focused on June, July, August, of course, summertime. And we looked at a few different models and stuff. So we started off with the RA5 reanalysis. We want to get a sense of how these events evolve in reality. And then we looked at a couple of different simulations. So we had a historical integration. These are atmosphere-only simulations prescribed SSTs. And then we had a warming simulation that was like a RCP, I should say this, SSP5-8.5, business as usual, technical scenario. And then we followed this heat wave tracking algorithm by Canadol. Basically, we looked at temperature on the lowest model level. We did a 5-day smooth because we want to isolate persistent events. We pull out a 29-day by 11-year running mean, and then we're looking for 90th percentile anomalies. So there's all these different ways to identify heat extremes. I don't want to get into that. This is just how we did it. All right. So just to get a sense here of the distribution of temperature in that region in the 90th percentile and above what we're looking at, we clustered together consecutive days to get individual events. And here's what the distribution of the duration. I don't think this is used. This is a different place. But we then focused on the 30 longest events. So we wanted to just focus on the longest duration events. With me? You fall asleep good? Okay, good. So here's our results. So just thinking about in terms of the duration of these events, I mean, work at GFDL, so we talk about the model, that's for sure. So the model seems to do a pretty good job in terms of generating the mean and the standard deviation of all of these heat wave events. But when you go and look at the distributions, you see that you're not really getting these long events as you are in reanalysis. So maybe that has to do something with the fact that we're not having this ocean underneath it. So that's one thing to point out. But in general, it seems like it's capturing the average pretty well. And then when we look at the warming simulation, there's a suggestion of a shift towards shorter events. So we want to explore that a little bit more and then get a sense of what the dynamics and the thermodynamics are doing. So here is the temperature anomaly. So you're going to see a lot of these plots that they're used to. This is 7 days before the event start, and the colors is showing you the temperature anomaly and how those evolve in time. So you can see that starting from 7 days before, you actually have a signature of a warm anomaly, and then it begins to decay a little bit, but then re-amplifies and really lingers around the region for a while. So now switching it up to the geopotential height. So the solid contours here, sorry for all these different projections, but here's the United States in the middle, here is Houston. So we're just looking at Houston for now. And this is the geopotential height anomaly. So solid contours are positive anomalies, and then dotted are negative anomalies. And we see that from at least 7 days before the start of these events, you have this signature of a quasi-stationary wave number 5 pattern that then goes some downstream development. So as you go forward in time, your upstream ridges and troughs begin to amplify, and then the ones, your downstream ridges and trough amplify, and your ones upstream begin to decay. And then you see that you have this persistent, amplifying high pressure over the region that just lingers there for a while. So this is in reanalysis. Let's take a look at how well our model is doing. So switching up the vibe to look at the model itself. And we see a similar kind of development, although some things are not the same. So we have this wave number 5 pattern, and we see this downstream development similar to the reanalysis, but the timing, the phase, the amplitude, and the wave refraction is not quite the same. But despite these differences, you see that these quasi-stationary waves really play a role when it comes to generating these heat events. Taking it a step further and then looking at our warming simulation, we see that our wave pattern is not as pronounced. So here you have this clear alternating high-low pressure, but here it's not so clear, right? So this could suggest that there's maybe greater variability and less predictability when it comes to these heat events in a warmer climate, at least from these simulations. Now these are not coupled simulations, but from these results we see that. And just looking further in time, how these events evolve. So now we're at 3 days after, going to 12 days after. And eventually you see that your wave pattern kind of starts to dissipate away, but the high pressure really lingers for a while. So it could suggest that other processes are really acting to maintain these events, and we wanted to take a deeper look at that. So we started to consider the temperature tendency on that lowest model level. So when we think about temperature tendency, in the model itself, you can say all these terms explicitly and get the budget to close. So the change in temperature with respect to time is a combination of the advection, so the air moving around, the diffusion, which is related to the sensible heating and the mixing of air as well, and then also latent heating, your short wave and your long wave radiation, of course. Here is what these fields look like in a snapshot. So your DT, I promise you, when you add all these things together, you do actually get this. It looks kind of crazy, but you do actually get it. And you see here you have this strong warming to the northwest from advection, and then a cooling to the southeast, and then your vertical diffusion term is acting to opposite to that, so it's kind of canceling out. So then much of your forcing comes from these other terms, such as your latent heating and your radiation terms. I put the short wave and the long wave together, but it's mostly from the long wave. So these are how these things evolved over time. In the interest of time, I'm just going to skip through this very quickly. Your advection looks pretty similar throughout the whole thing. Vertical diffusion is pretty opposite to the advection, but when we start looking at the radiation, you see that you get this strong warming signal. The green contours here, this is the Gulf of Mexico, by the way. I'm sorry, I had all these different projections. I hope it's not too confusing. But here's the Gulf of Mexico, here's the Houston area. The green contours is showing you the temperature anomaly. So you can see that you get this strong warming from the radiation that really lingers. This is mostly from the long wave. So the short wave, not so much. This is mostly long wave. And then when we look at latent heating, you see that you get a very nice, strong signal from latent heating acting to warm the region. And we took a deeper look at that. Why are you getting this latent heating signal? And when we looked at the soil moisture, you see that you get a lot of negative soil moisture anomalies. So your land is drying. That's giving you suppressed evaporative cooling, and thus adding to your heating anomaly that you get. So that was this part. What else we got? This is now the difference between the warming simulation and the control simulation of each one of these terms. So here's the advection, diffusion, in this second column, latent heating, and the difference between the two runs, and then these are different lag lead times. So the takeaway here is that there's some suggestion that in the warming simulation, you're getting more contribution from advection when it comes to these heat extreme events, and then perhaps less contribution from latent heating. So maybe those changes in soil moisture could be playing a role here. This is something we're still actively looking at, though. We also took a look at other regions. So we looked at New York. Of course, you got to look at New York. That's where I'm from. And in New York, most of the heat extremes are driven by advection, actually. And then Berenice, she's currently writing up her results. She found that in the Central Valley in California, she's Mexican-American, so she was motivated to look at places with a lot of migrant workers. And she found that they're really driven by advection and latent heating over there instead. So I guess the key takeaway here is that different places got different mechanisms that are driving the heat extremes. So I'll leave this up here for a minute. You can digest it. But basically, wave number 5 patterns are very important for generating these heat extremes. Advection and diffusion are acting to cancel each other out. So much of your signal in Houston is coming from latent heating and long wave. And then we have some suggestion in the warming simulation that the thermodynamics of these events might be changing. So one thing I really want to emphasize here too is this high pressure that sits over the region and really persists for a very long time, because we're going to dig deeper into these high pressure systems and switch up the vibe yet again. Are you ready? Are you okay? Yeah?
Sort of. Can I ask you a question?
Yes. Sort of.
In the simulations,
Yeah.
the wave structure doesn't look zonal at all. It looks more meridional. You know, you have alternating high-low anomalies in the meridional direction. Why are they almost polarized from the observations?
What do you mean polarized? Like very different?
Yeah, I mean, it goes way back.
Oh, yeah. That's a good question. I don't want to spend too much time on it right now, but probably that has something to do with the bias in the waveguide in the model.
Okay.
So because it's not structured in the right way, or it's not in the right direction, that's why you get these waves that refract in different ways.
Okay.
But that's a good thing.
So that comes back to the jet then, is that right?
Exactly. The waveguide jet,
Okay.
storm track,
Thanks.
that kind of thing. Yeah. Thank you. All right. So let's talk about blocking now. You know what blocking is? Okay, good. I'm going to tell you again. Atmospheric blocks are persistent, large, quasi-stationary, high-pressure systems. So here's a nice schematic from our colleagues at the National Weather Service. Basically, you have these high-pressure systems that really sit over a region, don't move around much, stagnates the flow, and you get warm, sunny conditions. And blocks are really bad, now let me tell you. They can have devastating impacts, the heat waves that I mentioned before, droughts. They can even give you cold spells. They can steer storms. Hurricane Sandy is a really sad example of that. And persistent storm surge as well. So we have a couple papers out about that if you want to check them out. But as Stephanie and I learned the other day, there's a lot of stuff about I guess we knew this, but there's a lot of stuff about blocking that we don't know, and we're still trying to figure out, especially as it pertains to climate change. So that's one thing that kind of drives me crazy, and I guess maybe not drive me crazy, but one thing that I'm very interested in. So first, I'm gonna just link blocking to the heat extremes with this paper that came out last year that I did. So what we're seeing here is some conditional probabilities and some regular probabilities. So in the contours, what you're seeing is the probability of atmospheric blocking in ERA5 reanalysis. So these contour intervals are in 2%. So here, for example, in the Pacific Northwest, your probability of getting a block there is about between 4 and 6%. But suddenly, when we look at the conditional probability, when you have these 90th percentile heat events, the probability shoots up to 50% of the time that you have these heat events, you have a block that's co-located. And you see there's a lot of regional variation, so maybe closer to where we are now and in the center of the country, there's not a strong co-location of blocking and heat extremes. But when we look at the Northwest and the Northeast, there is, and then also in the northern parts of Europe. So suggests that there's different mechanisms, again, that drive the heat extremes depending on where you're at. If we ramp things up to the 99th percentile heat events, we see that this co-location gets even stronger. So obviously blocks are playing a very pivotal role when it comes to heat extremes. And this is not new information, we've known this, but it's a nice quantification of that. So with that being said, let me ask you a question. When we go to a warmer climate, what do you think happens to the blocking? How many people say that there's more? Raise your hand. Okay. Okay. How many people say that there's less? Wow, most of you don't vote. Listen, we're scientists here. We gotta be braver than that. So I would guess that there would be more, but actually that's not the case. There's actually less. I can't believe all you people didn't vote. Come on, we're trying to engage here. But all right, so this is how the probability of blocking changes in a warmer climate. So I think this is the coupled model now. This is our coupled CMIP6 model, CM4. And you can see the blue is showing you the difference in blocking. Almost everywhere you have a big decrease in blocking, especially on the northwest and northeastern flanks of the country, and then over the Pacific. So there's a decrease in blocking in the warmer world. And then also your association of blocking, so now your conditional probabilities also decreases. So this suggests that when you go into this warmer climate and you have these 90th percentile heat extremes, they're less driven by blocking and more driven by something else. And I did this work before the work that I just showed you, and this was kind of the motivation for doing that other piece. Even though I was looking at different areas, but yeah. So one thing I've really been thinking about lately too is like, why is there less blocking? So we saw that in summertime, you get this decrease in blocking, but also you see this signal in wintertime as well. And this is sensitive to the different ways you identify blocking, I gotta say that. But this has been a pretty robust signal ever since like CMIP 2 or 3. So I wanted to dig deeper into why that you have this kind of response. So we did some experiments. And we did some prescribed sea surface temperature experiments because we want to kind of simplify things a bit more. So starting off with our, wait, did someone say something? No, I'm just tripping on hearing things. Sorry. So this is our historical simulation and what the SST looks like in that. It's just like the annual mean of SST. And then we took that same SSP5, that 3.5 scenario, and created a prescribed SST data set from that, just averaged all the years together. And you get this change in SST, so obviously it warms pretty much everywhere, but then you see there's a change in the SST pattern as well. So we wanted to decompose that. And you can take your change in SST here, so your warming minus your control, and then your SST, you decompose it into something called a tropical mean. Well, it's arbitrary. It's a mean plus some change in the SST pattern. In this case, the mean that we used was the tropical mean. So between -30 and 30 degrees, we took the average temperature change and you get like 3 degrees. And the reason why we only took that region is we wanted to get the change in the SST pattern relative to that tropical mean. So we didn't want to include the effects of Arctic amplification when we calculated that. So this is what the change in the SST pattern looks like. And then we did some experiments. So of course we have our control simulation, which is this one basically. And then our first experiment, we put this entire SST change with the warming, with the change in SST pattern, and we ran an experiment. And then we did an experiment where we did a uniform warming. So we took this top one and we added this 3 degrees everywhere. And then in our final one, we changed the SST pattern without this warming. So we did this one and then added the change to the pattern. Does that make sense? Okay, good. So how we track blocks too, I should mention that. We took a 500 hectopascal geopotential height metric. And in this case, we look for strong anomalies that also reverse the flow. So they reverse the gradient of geopotential height. So what did we get? How long do I have to talk until?
We have until 4:30, including questions.
4:30? I got a long time here. All right. Sorry, guys. All right, so yeah, I guess long story short, the key takeaway here is that the uniform warming was driving most of the response. So here is the response in the full simulation that includes both the warming and the pattern change together. And this is what you get, and then this is just the uniform warming zonal mean temperature response. So you get this strong upper tropospheric warming signal that's very characteristic when you look at these warming simulations. You see that it's not quite exactly the same though. In the mid-latitudes, for example, you don't have this part where you have a very uniform vertical profile in the change. But when you go and you look at the pattern simulation, that kind of fixes things a bit. And then looking at the zonal mean, zonal wind, you get a very similar kind of response where the uniform warming is dominating the signal. So that's one of the key takeaways here, is that the uniform warming is dominating the signal. Now just looking at the jet, looking at the lat long plane at 250 hectopascals. And again, we see that the changes in the zonal wind at that level is very much explained by the uniform warming. So you get this kind of Crosby wave train that emanates out of the tropics and alternates this increasing and decreasing as you get towards the pole. Your pattern change is also shifting things too though. So don't discount the effects of that. And then when it comes to the blocking, you get a very similar signal. So I guess one of the key takeaways here though is that the uniform warming really drives the circulation changes and the blocking kind of follows suit. So when you look at the full response, it's very similar to the uniform warming where you have this decrease in blocking by Greenland and the eastern part of North America, and then also on the west coast of the continent and over the Pacific. So even this little increase here you're getting as well. And that is without the pattern change. But you also see that the pattern change does play a pretty significant role. It also acts to decrease blocking. And if you remember back to what the pattern change looked like, it's an El Nino-like kind of pattern change. And this is consistent with El Nino and blocking, because when you have El Nino, you get less blocking in this region. So all of this is consistent, but you see that there's a nonlinear behavior, because when you add these two things together, you get a decrease in blocking that is less than what you get in the full simulation. So there's some nonlinear behavior going on that's very interesting. So from this point of view, it seems like the uniform warming is really driving the decrease in blocking. But we wanted to take it a step further. And originally when I submitted this paper, I didn't include this next part because it was hard and I couldn't get it to work. But then the reviewers got mad at me and they were like, yo, you gotta explain the mechanism. So that's what I did. And luckily, we were able to get it to work. So we took this energetics kind of framework. It's from a paper by Patrick Martineau that came out recently. It's originally from Ort in 1964. But we looked at basically the transformation of eddy energy in blocks and how it extracted energy from different aspects of the atmosphere. So you can take this energy budget and it's composed of different terms. So you have baroclinic conversion. So this is your blocking energy, basically your potential energy, and then your eddy kinetic energy. And that energy is fueled by baroclinic conversion, so extracting mean state potential energy into your block. And then you have your barotropic conversion, so extracting mean state kinetic energy into your blocks. And then your high frequency transient. So when I say high frequency, I'm saying your 10-day high pass filtered eddies. They can contribute thermal anomalies to your block that act to reinforce them. And then you have your momentum anomalies as well. So, and then of course your diabatic effects and your residual, where if anyone has worked with the budget, you just lump everything else into the residual. No big deal. So we took a look at that. Here's the equations. So you think that I'm smart and I know math. So when you look at the baroclinic conversion, it's a function of the stability, also the blocking anomalies themselves and the gradient of the background temperature. And then your barotropic conversion has to do with the strength of your eddy, your blocking eddy, and then also the gradient of the background flow. And then your high frequency terms, so you take your 10-day high pass, and then it's a bunch of time filtering. And we're able to calculate an efficiency from each one of these processes. So here's your eddy available potential energy, here's your eddy kinetic energy, and then we can calculate an efficiency. So we take each one of these terms, we put it on the numerator, we put the total energy on the bottom, we integrate it over the whole northern hemisphere, because you want to get rid of the advection term and then also the vertical motion part. And then you can calculate an efficiency. So here's what each one of these terms look like in composites. So here's your baroclinic conversion for blocks just inside of this box right here. And you see it's a stronger signal than the other ones. Your barotropic conversion is on the bottom. Your high frequency eddy forcing is much weaker than your mean state energy extraction. And then basically we took this box and we moved it everywhere around the northern hemisphere, and we made the calculation of the efficiency of each process. So that's what this is telling you. The places where it's white is that where you didn't have enough events. But we see that baroclinic conversion really dominates when it comes to energizing atmospheric blocking. And this is consistent with what Patrick showed in his paper. You also get some nice contributions from the barotropic conversion, although it's not as strong. And there's definitely a regional variation to all of this. And then when it comes to the high frequency forcing of the thermal anomalies, so C, that's acting to dissipate things, cool things off. And then your high frequency forcing from the momentum anomalies, those also act to reinforce the blocking, but it's not as strong as the baroclinic conversion. And then your residual term, this acts to dissipate everything away. So then taking it a step further now, this is in our control simulation, the contribution from each one of these terms. Now we're going to look at the difference between the control simulation and each one of the other experiments. So over in North America, we see, so the white contours now are showing you where there's a decrease in blocking, and basically almost everywhere you have a decrease in blocking, you have a decrease in baroclinic conversion. And in some other plots that I don't have in here, I suspect that it's probably from a more stable atmosphere, so you're less able to extract this baroclinic energy. But if you look over the Pacific, you have a decrease in blocking, but you don't have a decrease in baroclinic conversion. But then you go look at the residual term and you see that that term actually decreases over the Pacific. So it could suggest that you're getting more dissipation in that region, maybe from evaporative cooling, acting to get rid of the thermal anomaly. So that's one result. So this is in the full simulation where we had both the warming and the pattern change. Now in the uniform warming simulation, you get a very similar kind of response where baroclinic conversion is decreasing in most places, and then over the Pacific, where you have a decrease in blocking, you get a decrease in your residual. And then coming to the pattern effect, you see that where you have your decreases in blocking, this is actually mostly driven by decrease in barotropic conversion. And I've been working on some idealized ENSO simulations where we're looking at Eastern Pacific versus Central Pacific ENSO and how the blocking responds to that. And we find the same signal. You get a decreased barotropic conversion in those cases as well. So that plays a role. And I think that's pretty much it for this part. I know I went through that really quickly, and I'm sorry. But I hope you understood something. What did you think? Is it crazy? Was it boring? Thank you. So you digest for a minute, because I'm gonna switch up the vibe. It's gonna be totally different, so give your mind a chance to reset here. Okay, you ready for the next
So,
part? Oh, I'm
Can-
sorry.
Can you give like some kind of explanation of what, you showed the math, but you didn't really give like a schematic or like a picture of what you mean by reduced baroclinic conversion or enhanced diabatic dissipation?
Oh, yes. So the
can you give, like,
diabatic,
sort of a mechanistic.
the diabatic dissipation, that part comes, so we're actually not able to calculate that directly in these simulations because I didn't save the terms, but that's something you want to look at. We can break it down. Those same thermodynamic terms I showed you before, we have other simulations where we did save them, so that's something we're actively looking at. But in terms of the baroclinic conversion, what is happening is you have this temperature gradient where the block is in the mean state temperature, and from that temperature gradient, the block itself, the blocking anomalies, it's pulling energy from that gradient to sustain itself, but the extraction of that energy is dependent on the gradient itself, the strength of the block, but also the stability of the atmosphere. So in our case, we have a more stable atmosphere, so it's less efficient at pulling out that energy.
Okay.
Yeah, I hope that quite answers your question, but.
It does, yeah.
Okay.
Isn't that because the jet's further north? Because the jet divides poorly stratified air to the south in our hemisphere from more strongly
Yeah.
stratified air to the north. I mean, is that part of what's going on there?
It could be, because when you look at the background gradient of temperature, that also kind of dictates where the jet is as well,
Yeah.
because the potential vorticity gradients. So it could be that. I mean, I'm trying to figure out how I can decompose that baroclinic conversion into the separate pieces. I mean, I suspect that it's because you have a more stable atmosphere, but it also could be where the jet is shifting.
Okay.
You have a question, sir?
Yeah, for the Houston
Yeah.
heat case,
Yeah.
so I like the tie with the soil moisture,
Yeah.
but you have a soil moisture deficit.
Yes.
You have a blocking high,
Mm-hmm.
but it was a positive latent heating. Where?
Yeah, so I think that one has been something I've been thinking about too, because I mean, if you have a positive latent heating there, then it means that it's raining, but obviously it's not raining. So what I think is happening, because we're looking at lowest model level, I think it's just taking what the land is doing and it's saying, oh, the land has this strong positive latent heating because of the soil moisture deficit, so you don't have that evaporative cooling, and the atmosphere is just going to follow along with it. So that one we're still digging into.
Okay.
But yeah, it might just be like a model thing. Yeah. All right, so let me move on to the next part, just so we have enough time here. So like I said, we're gonna switch the vibe up. And I want to show you this nice picture of this nice workshop that I went to. Had a wonderful time. Learned a lot of stuff. You had a nice time, Stephanie and Sarah, yeah? It was really good, learned a lot of cool science. And I go to these things, I have a nice time as a researcher. But I'm always left with a sadness and an emptiness when I go to these things and conferences, because there's not a lot of diversity. You know, out of this picture with 94 people, there's one black person. There's 2 Hispanic people, and that's not what our country looks like. Go outside and look, Cuba doesn't look like that. So why is it that our science looks like that? I mean, we know why, but what can we do to make it better? I sit here and complain, but I'm focused on making things better. So this is what the next part is about, like it or not. So let's start with just the population of the US, right? So this is from the census data from 2023. 13.5% of our country is black. We got 1.3% Native American. Then you got your Native Hawaiians, 0.3%. Your Hispanic and Latino, that's 19%. And it's probably even more, actually, because you think about people that are undocumented. But then, as someone who works for the federal government, NOAA published our demographics recently, and it's only 9% black and 5% Latino. So obviously that's a problem. If we're here to serve the American people, but we don't look like the American people, then that's an issue. And I would say that GFDL is even worse than this. We're only 6% black and 2% Latino. So what can we do to make things better? This is the issue of underrepresentation that you hear all the time. And we've known it for a really long time. I found this paper from NOAA that was from 1978 talking about this, and really nothing has gotten better. It's very sad. But now I'm here. So we do what we can to make it better. And I'll just contextualize things a little bit more by telling you a little bit more about my story, because I love to talk about myself. So this was me back in the day in my element. I never really wanted to be a scientist, actually. I did my PhD in physics because I wanted people to think I was smart. That way I can help kids. So this was me towards the end of undergrad, and this is me in my element. Bringing kids to City College, showing them these physics demonstrations. A lot of these students come from the Caribbean, immigrant families like myself, so it was really great to connect with them on that level and show them a different pathway in life. So that was my thing. I'm gonna go do a PhD in physics. People are gonna think I'm smart, they'll listen to me, and then we can help all the kids in the hood. So, went to do my PhD. My professor got mad at me, my advisor, he was like, V, you know, do your PhD and then you can become rich and open a foundation. Don't do this stuff. And I was like, yo, but I really like this stuff and it's really important to me. And he was like, I see that it invigorates you, just make sure you get your work done. So that's what I did. And then he became very supportive. And I took all these classes in science education. One thing about going to a minority-serving institution is that all of the coursework is framed around the minority experience. And I took all the courses to get a science teaching certification, because I was like, I'm gonna go work in a nonprofit after this. And I showed you my bad grades, here's some of my good ones. And I took all these crazy classes, right? Quantum mechanics, geophysical fluid dynamics. The best class I took was this one, Intro to Inclusive Education, where you learned how to work with students from all kind of different backgrounds and, I guess, superpowers, as I like to call it. So that was a really, really dope experience, and I feel like I learned more from that than any fluid dynamics class. So I took this very seriously. If you go look at my thesis, there's a whole chapter about a project I did with the National Society of Black Physicists, where we started a mentoring program for young people of color in New York City. And we mentored them. I did some qualitative analysis, so interviewing them, extracting themes from their experience, and that was really dope. And it led me to where I was today. And I would say too, like, I never wanted to become a scientist because I didn't think I was smart enough to become a scientist, is the thing. But these two guys really helped me realize that I am smart enough to be a scientist and I can do anything I want in the world. I emphasize these two guys because they're very different from me. This is Jimmy, my PhD advisor. He's a white dude from Kentucky. And this is Yi. He's a Chinese dude. So they were very nice to me. They showed a lot of belief in me. And man, I would say these guys have done more for me than my own father. So couldn't have done it without them. And I gotta shout them out every single time. So they convinced me that I was smart enough to be a scientist. I had a job lined up as a nonprofit, but Yi convinced me to do a postdoc at GFDL. He was like, you can get these jobs anytime, but just try to do a postdoc at GFDL because it'll open up doors for you. And I was like, all right, I'll listen to you. You seem pretty smart. So I did that, and here I am now. So now, let's think about what it takes to become a scientist. Obviously this is not like general theory for making people scientists, but this is how I like to think about it. I categorize it into two things. Your expertise and proficiency. So of course, this is your like run-of-the-mill stuff, your foundational knowledge. Your coursework, your reading, your reviewing, you're engaging with other scientists, the literature, going to talks, conferences, speaking with other scientists, things like that. You're also learning the skills, so learning how to code, how to go out into the field, take measurements, whatever it is. And then, of course, the ability to produce and present new contributions to the field. That's very important to be a scientist. And then self-efficacy. This is a really hard one to teach, but with the right kind of guidance, we can teach it. But motivating people to motivate themselves, essentially. And then, aside from all this stuff, I mean, it's the run-of-the-mill stuff, right? There's also the sense of identity and belonging, right? So you see yourself as a scientist. For some people, that's easy because there are scientists that look like you around you a lot. For me, not so much. But an important thing is that other people see you as a scientist too, and they give you that validation. I got that a lot from Jimmy and Yi, but I also got it a lot from other people at GFDL. I remember, now it's story time, because I was going through all that science, now I'm going to tell you a bunch of stories. So I remember, first time I gave a talk at GFDL as a grad student, I had all these people who signed up to talk to me, and I didn't know who any of them were, because like I said, I wanted to be an astrophysicist. go and give my talk, and this bald-headed Indian dude comes in the Zoom call, and he starts asking me about cricket and all this stuff about life. And then he was really cool, really nice to me, and then he was interested in my work. He gave me some feedback, gave me some encouragement, and then I look up who he is, and it's the director of the lab. He's got like 30,000 citations, and it's like, there was him, but then there was also other people, Steve Griffiths, you know, Balaji, all these amazing scientists who showed their belief in me and just gave me the time of day. So that validation is very, very important. Now, this also ties into the community of support around you. I had all these great scientists supporting me, but I also had my friends, my homies that I, studied with, and then we go out and go to the bar with after. That's important. So all the grad students, make sure you make friends, postdocs, things like that. My parents, of course, everybody in my family. But then unfortunately, when it comes to being a minority of any sort, whether it be your color, disability, gender, whatever, right, sexuality, whatever, you have to sometimes avoid and overcome, you can't always avoid them, unfortunately, microaggressions, stereotypes, racism, systemic barriers, and feelings of isolation. A minority student, for example, the students complain all the time, very rightfully so, that they can't afford to live in certain places on their graduate student stipend, and then some of them, on top of that, have to send money back home to support their parents, like I did. My dad lost his job, he suffers from addiction, so I had to help my mom to keep a roof over her head. And these are the types of things some of us have to deal with, unfortunately. I mean, everybody deals with their own challenges, that's for damn sure. But some people definitely have more challenges than others, and we gotta acknowledge that. And I feel like another important thing when it comes to a sense of identity and belonging is just bringing it back, connecting it back to your own world. For me, I mean, I could have gone and studied astrophysics. Is there any astrophysicists in here? Okay, good. I'm glad I ended up doing something more important, I think, because I can go back to Trinidad and talk to my uncles about climate change and how they're from a fishing village, so how it affects their local economy. So this was very important to me, and what ultimately made me decide, like, I'm a climate scientist. So if you want to read more about this, there's some really great papers out. This is a really good one to start. It's a review paper, and basically all the references in there are really good to look at. And then if you've heard of the UCAR SOARS program, that's a really excellent model to follow. So that's kind of some of the background. Now let's talk about some of the solutions. What are we doing at GFDL to make things better? And we kind of put it into 3 categories, where we're recruiting, we're mentoring, like really mentoring though, not that BS that some people would be doing. And then, I wasn't even making a joke. This building community as well. So I'll just touch upon each one of these things. I'll rush through this part though. So just thinking about recruitment, we've been really focused. So I got hired at GFDL in September. 50% of my job is diversity, equity, inclusion, 50% is research. It's the first job of that kind in NOAA. Hopefully, if I don't mess things up, there'll be more jobs like this. And we've been working really hard to support NOAA's network with minority serving institutions. So this past AMS, Yi, my mentor, he connected me with Hector Jimenez from University of Puerto Rico. And then I was like, Hector, let's meet up with your students. Let's have them meet some NOAA scientists. So we had this NOAA booth meetup where we met with the students from University of Puerto Rico, and we talked to them about being NOAA scientists and doing research, but then also life, and showed them that we're real people also, and we come from the same background as them. See a lot of smiles on my Boricuas here. So that was really dope. And actually one of the students, she's in there, somewhere in here, Stephanie, she's coming to do an internship with me and some of my friends this summer, Andrew Williams and Notter and Tim Merlis. And so that's one thing that we're doing. We're trying to build more collaborations with UPRM, of course, and then also visiting these institutions. So we went to Hampton University this past fall. We spent 2 days there. First day, we focused on professional development. We did a guest lecture in one of these classes. We talked to undergraduate students about our career pathways and becoming scientists. And then, of course, we talked about hardcore climate modeling the next day. That was really dope. And then from that, we're building our research collaborations. And I think ultimately, you know, it's a business at the end of the day. Academia is a business, so whatever you can do to help these institutions raise money, we're trying to apply for some funding with them. I'm on several proposals at the moment. So that's what we're doing. Mara's doing some funny stuff back there. And also tapping into professional organizations. So we've been doing more to work with National Society of Black Engineers. So we've gone to their conference the last 2 years, and we present about NOAA, of course, but we're taking it a step further and we're really immersing ourselves. Our guy Lonnie here, National Society of Black Engineers, they have an environmental special interest group. Lonnie is one of the leaders in that group. So we're also directing how these organizations go and kind of intertwining NOAA's role into that. So this is one of them we're working with. SACNIS is another one. And I'm working on trying to loop in National Society of Black Physicists because of my connections there. So there's that. Definitely get out there into the community. Some kids are lucky because they get to go home at the end of the day after school and talk to a scientist because their parent is a scientist. My kids eventually will be able to do that. That's great for them. Me, on the other hand, I did not have that luxury. I came home from school and no one was there because my mom was at work and my dad, he was just doing whatever. So, you know, we try to expose these kids at an early age to science. We do a lot of local work in the community. So this is at the Boys and Girls Club near GFDL. So definitely get out there into the community. And the gentleman I talked to this morning, Mike, was really dope. The stuff that he was doing with the autistic kids, I really love that part. So, you know, minority is not just about race or gender, but you gotta think about, you know, superpowers as well. So, mentoring now. So mentor with purpose and clarity, and I said really mentoring people. And I think that starts with getting to know each other. Who are the students that you're working with? What do they like? What are their interests? What are their goals? How do they see themselves in this world? This is very important. Identity, right? So get to know each other, set expectations. Do they need to meet every week? Do they need to not meet? And you just meet with them whenever? And then identify their strengths. I'm not going to say weaknesses, but I'm going to say places to improve. Maybe you're setting weekly or monthly or semesterly goals. And I would also say that a very important part is to be compassionate and allow people some grace. Remember when I was talking to Angel this morning, this guy freaking made me cry. And the talk that came up was that a lot of students, they come in with extra stuff, extra trauma that you don't see on the surface. So me, for example, Jimmy had to be very patient with me because I mentioned all these daddy issues that I have, and it was really bad growing up. I'm not going to get into details, but it was really bad. And he allowed me the grace to, you know, take a step back when I needed to, but then also, you know, you still gotta finish your degree, and then you could really make a greater impact in the world. So allow people some grace. Definitely mentor to develop the whole person, not just the science. So what I like to do when I mentor students is set these weekly science goals, but also these professional development goals. So things like how do you network with other scientists, how do you write a CV, how do you apply, how do you practice self-care so you don't drive yourself crazy, things like that. So mentor the whole person. And then one thing we're really trying to do is build a community of mentors around our mentees at GFDL. So Stephanie, for example, when she comes in the summertime, not the Stephanie Ortiz, when she comes in the summer, there's Andrew, then there's me, then there's Nader and Tim, but then also everybody else in our division who is surrounding her to help build her up and get that confidence in her so she feels comfortable. And then finally, we want to build community. So you want to create opportunities for people to interact, that's for sure. It seems like you all do a really good job, so maybe I'm preaching to the choir here. But make sure that everyone is comfortable, seen, heard, and included. You might be having a social event for your department. There's someone who's introverted over there, not really interacting with anyone. Go up and talk to them, invite them into the conversation, get to know them, involve them. So at GFDL, one thing we've been doing lately is this pumpkin decorating contest. That's been really fun. We also love a cookout. And then these smaller kind of interactions can be very powerful as well. So in this case, here's our seminar speaker, Shayla. She's from Dominican Republic. She does seafloor mapping. And here's the interns. And we said, interns, you want to go have a lunch date with Shayla? And they're like, hell yeah. So things like that are really good. And then also, one thing we've been working on, here's Andrew here. Andrew has been very pivotal in this, along with others from GFDL, Nicole, Elon, Ming Jing here as well. Obviously, as scientists, a lot of us are introverted and may have difficulties, making friends or talking to other people. So we've been kind of hosting these small talk events where we're giving people some icebreaker prompts and sitting them around to talk to each other and get to know other people in the lab, but also develop their social skills better. So these are all like good vibes kind of things, right? What do you think? Now I'm gonna switch up because we also gotta be real about it here too. Because there's a lot of nonsense that goes on. And we cannot tolerate that stuff. When we are in science, we have to create a safe space with zero tolerance for prejudice, harassment, and disrespect. And it's important that we do not stay silent. It might happen to you, and you're afraid to say something, but you have to. You don't have to, but you should. And it takes a lot of bravery to do that, and you might be scared of retaliation, but nothing will change if you stay silent. And then also, if you see it happen, especially if you're coming from a place of privilege, you don't stay silent. You got to say something. I'll give you one last story. I was at this conference the other day with 30 very renowned physics people. You know the physicist crowd. Very renowned people. We're talking Nobel Prize winner, billionaires, New York Times bestseller, and walking with the guys. You have to be one of the guys for that moment. And then there's a young lady in front of us. And then one of them, leans over to us and he's like, "Oh, it's too bad she's a lesbian." And then I look at him and I'm like, "No, bro, we're not doing that. We're not doing that. This is a professional environment. Nobody is here for that to be disrespected or anything like that." And I think I, made some people not like me that day, but I don't care because we're not tolerating that. And fellas, especially, if you see any sort of discrimination towards women, sexualizing, everybody's here for the same reason, to be a scientist, to make the world a better place, not for any sort of harassment. So with that being said, I would just mention, going back to the good vibes, at the end of the day, we're all just people. We want to vibe, we want to have fun, do good science, do positive things in this world. So when you're creating community, just vibe and have fun. You got some of my Caribbean people in here, and they know all about having fun, so tap into that. And yeah, so again, thank you all for welcoming me into your community. You all are really awesome. I think out of all the places I've been, this is my favorite. So hopefully in the next 30 minutes that doesn't get messed up. But I'll leave this up here. Thank you. Angel?
Great talk, by the way. Really entertaining. Love the vibe. Just love the honesty.
Thank you.
Breath of fresh air for me. So a question that I have for you is on the building relationship side. One thing that you want to kind of like hook your brain at is that so with mentoring, it's important to get to know each other.
Mm-hmm.
And one of the challenges, and particularly in academic circles, but in any kind of circle with professionals, is the gap between the mentee and the mentor in terms of professional development and age and so forth. And often I feel like it's a challenge to have the mentee get to know the mentor and know them as a human being and give that compassion and grace on the way back.
Oh,
and
that's
I think
true.
that this is especially challenging for mentors who are from underrepresented groups who may have a similar situation, right, where they have family challenges, personal life challenges, they're giving money to families back, and often those things are actually never spoken about, right, because when you're in an academic circle, those are not things that are actually even talked about, or even serviced, right, that are not necessarily like valued to the degree that they should be. So how would you approach the challenge of like getting into this group and kind of like opening, getting to this kind of ice-breaking moment in which the exchange and getting to know each other is actually mutual and not one-sided?
Yeah,
Fair.
I mean, you're speaking to a deeper issue culturally when it comes to academia, where it's like, this is work and that's it. Like, you're not a human outside of work. You just do science and that's it, right? And I think, especially now, we gotta switch that. We gotta switch that. We're humans too. You saw that I shared my identity in the beginning, and I think part of it too is making yourself vulnerable and having those conversations. One thing that was really great with Jimmy is, you know, every so often we go out and grab beers, and the rules was no talking about work. We just talk about life and vibe. And he also shared some challenges that he went through. So it takes also making yourself vulnerable and being brave. And then also, I would say too, lean on that community of mentors. I know you have postdocs in your group, so maybe your postdocs are doing some of the mentorship, and people have different kinds of relationships, so everybody is learning together. But I think the biggest thing is just the bravery of making yourself vulnerable and sharing with that. And then you never know, I mean, I think you're very open about sharing some of your struggles, and probably a lot of students share that as well, so it might resonate with them. So, you know, don't be so hard-skinned and hard-shelled. It's okay to be a person, that's for sure. And then spend some time with them, you know, go out, have fun, things like that. Rosa?
Amazing.
Oh, thank you.
I think that like the role you're playing is so important.
Mhm.
But like you said, it's like the first in NOAA. So I'm curious as to if you have any like insight on how to move more systemically to have more positions like this in different places like NSF, NASA, I don't know, like more broadly, so that these types of efforts are more like, I don't know, yeah, applied more systemically within the field.
Yeah, I think, sorry, I drank a tea earlier, and it's giving me a lot of gas here, man. Okay, so, first of all, this is one way to do that, so thank you, Stephanie, for inviting me in the first place to come here and be able to share this with you all, whether you enjoyed it or not, but just giving people the platform to share that you're a scientist, but you also care about social and systemic justice. So, I think, yeah, the more I can spread my gospel would be great. A large part of it is funding too. These funding agencies need to be able to, they need to advocate funding towards these things. We had a OAR, Office of Atmospheric and Ocean Research, meeting the other day, and they were talking about all these budget cuts in NOAA, and I was like, well, what are you gonna do to the DEI piece? Are you gonna cut budget there? And they were like, well, that doesn't get a lot of money, so that'll probably be okay. And I was like, well, that's great, but they actually need more money there. So we need to put more money towards these kinds of things. I recently submitted a proposal, as you know, to get more people like me and train them. So now I have a postdoc coming in the fall, where she'll be the first Black person to ever be a postdoc at GFDL, which is good and bad at the same time. But you know, I'm training her because when I told her about my job, she's my friend, and when I told her about my job, she was like, I want to do that. And and what I'm trying to do is like train more people to be in this kind of role like me, apply for funding to hire people like that, and yeah, spread the word. I've been trying to talk to people in NSF and NASA to tell them more about what I'm doing. That way, hopefully more organizations think about this. And I think also professors too, you can, although maybe the universities so much don't really care about the social justice thing, they say they do, but at the end of the day, it's not bringing in a lot of money. But who cares? Once you get your tenure, you do whatever you want, so just do it. Yeah, you just gotta get out there and do it. I think you're well on your way though, Rosa. I look up to you when it comes to that stuff. Yeah.
Maybe really good talk, and
Yeah.
I could relate to a lot of stuff you mentioned.
Mhm.
One thing that I came across during another talk and when looking at literature about this diversity thing is that there's not enough data available on this, like NSF or NASA or NOAA websites, which actually you need to publishable research about like race or sex or gender and stuff, and how much proposal they're getting, etc. Not, even though they have the data. So what as prospective scientists and current scientists we should do so that that data is more accessible, which is lying somewhere, but it's not accessible.
Yeah, that one's a really complicated issue because that's also regime dependent, depending on the people in power, right? So certain administrations, certain presidential administrations, for example, care more about these things than others. I can't be too specific, but you know what I mean? So that's one issue regarding that. And then I think a lot of the issue too is that these people don't put the information out there on purpose because they don't want the backlash that comes along with it. So I think, I don't know, what can you do? I guess some sort of protest or call them out on it, you know, during these town hall meetings, stand up, like, why don't you publish this data? That NOAA figure that I showed you earlier, it was pretty hard for me to find that. And that's from 2021. I couldn't find a recent one. We have internal ones that we share, but I can't put that up, obviously. So I think, yeah, putting pressure on these people to share that kind of thing, putting pressure on program managers, program directors, and then just in a grander scale thing, voting for the right kind of people that care about these kinds of issues. Yeah, it's hard. It's hard.
Stephanie said that you had started your own company. Have you been able to go back and realize your dream of being an educator?
So I have a company that I started during my PhD, and that's been going really well. And yeah, my company is a little bit different because it's about making money, I'll be honest. But I do, so there's like a tutoring and test prep component of it where we work with wealthy people, but then I also get these consulting jobs where, I'm not even sure if I'm allowed to talk about this, but I get these consulting jobs where I help programs in underserved communities build themselves up. So I've done a little bit of that. But also recently I've started a nonprofit organization with some of my friends called Caribbeans for Climate. Actually, Myra was on our panel the other day. It was called Celebrating Caribbean Women Leaders Leading Climate Action. And what we're trying to do there is empower more people from the Caribbean to get interested in climate science, show them academic pathways, and then build collaborations within the Caribbean. So in my dream of being an educator, I guess I'm fulfilling it. I mean, it's not traditional in the sense that I'm not a professor standing up in front of the classroom, and although I did have a job offer to do that when I was trying to decide, but I ultimately decided to go this way because, I mean, this is the biggest institution in the world, the U.S. federal government. So I felt like I could make the most impact here, and I can be an educator, not by standing in front of the classroom per se, although we do that. We do go to these minority-serving institutions, and we're teaching actual classes, like helping guest lecturers on the actual topics in the class. But also, I think on the mentorship side, which has been really key. Myra's done a lot to motivate me in that sense from when she was at NASA. But I think, yeah, mentorship is a really great place to be an educator. Yeah, thank you.
Can I ask two questions? One on part two and one on part one?
Sure.
Okay, part two is less well worded. Something I think about a lot is how, for me, it's been very different with trying to help out on issues of diversity, equity, and inclusion. Back when I was at NCAR as a more junior scientist versus as a professor, because, well, I mean, there's lots of differences. It's a different institution. It's a lab versus a department. I'm now have to be more cognizant of where I hold power and could be silencing someone unintentionally. So I have to somehow think about how I act in situations. And I'm just kind of curious, because you've gone from an academic institution to a lab. What differences do you see on how those two different roles play out? How the different institutions differ between a university versus a lab?
Yeah, that's a really good question. So, kind of have to be careful how I answer this though. Yeah, when it comes to academic institutions, universities, they may say a lot. You think about what happened with George Floyd, and there's all these people that all of a sudden care about diversity, and that lasted for maybe a summer, and then after that, it's like back to your scheduled programming. So there's a lot of lip service, and what's really reflected in advancement of DEI is like, show me your hiring portfolio. How are you hiring people? How are you dealing with DEI issues? What are your actions? So a lot of it just has to do with the administration. If you have an administration that genuinely cares about that stuff, then you will become better. But if they don't and they're just saying, then it's hard to make any sort of advancement. Luckily at GFDL now, we have a front office that seems to deeply care about this stuff and have provided a lot of backing. I mean, they hired me, so that's a good start. So definitely it starts with the administration being able to support this. And then in our case, as a federal lab, that came from the government. So there was a lab review a couple years ago, and they said, like, yo, you guys are doing bad with diversity, and you gotta do better. So that was told to them by higher up above them. And then that came from, you know, the administration, whatever, I guess, yeah, Biden administration. So, yeah, for the federal government, it really just depends on, because I mean, the election could come in November and then maybe I get fired, who knows? But yeah, so I would say just like wherever you end up at, I think here it seems very supportive, I guess. So just be cognizant of the administration. If they're giving you a lot of pushback, then maybe I'll figure out a way to dance around what they do and appease them. A lot of it is like politicking, that's for sure.
And then part one question, so it looked like back when you're looking at that, that progression of highs and lows and stuff.
Yeah.
Is that a circumglobal teleconnection pattern? Is it,
Oh, it pretty much is. So one thing that we've been thinking about is we just got this code working to quantify the wave envelope amplitude of quasi-stationary waves. And I didn't put them in here, but I do have some preliminary figures looking at that. Sorry. A long talk. I'm sorry about this. Probably should have just did the other way. Yeah, so right here.
yeah. It's like I'm thinking of papers by
Yeah,
folks
right
like
here.
Honey and Tang where they call this thing something that looks
Yes,
like this.
yes.
Is it the same thing?
Yes.
Cool.
Yes, it is.
Is
Yes.
there any ideas for why looks like, I guess, AM4 can't quite capture it, or is it?
Oh, that's a good question too. So part of it in the high-end tank paper, one thing they were thinking about was the soil moisture feedbacks really can act to reinforce these circumglobal patterns. And then I think, like we were saying earlier, a lot of it has to do with the mean state and capturing that properly, because if you're not capturing the jet properly, you're not capturing the waveguide properly, so then you're not able to get the full behavior of the waves. Yeah, and I think a lot of times when it comes to model development, we're thinking about like tuning stuff according to like what the tropics are doing and the radiation and the clouds and that kind of thing. But like the mid-latitude, that's like, hopefully is good, you know, so don't think about it too much.
You got that right.
Yeah, yeah. So I guess maybe this is part of why I got hired as a specializing in mid-latitude dynamics, is how can we make our capturing of mid-latitude dynamics better? Yeah. This also could do something with the fact that we don't have a coupled ocean. So definitely, that's a good research question. Any other questions?
I'll just make the comment, V. I'm really encouraged to hear you say you've had a good visit here, given your interests in both the science as well as the community of scientists that we have in our field, because I think we do a good job at both. And I think that's not by accident. You know, I think a lot of times a person can judge a department from a distance by who is on the staff, who's on the faculty, and what their research is. But when you get right down to it, it's what the people are in the department. And I mean all the people, from the office staff to the undergrads, all the way up to the top. And this place is functional. And we've figured that out, and I think this is a nice paradigm for those who have spent some time training here to bring out to the community. It can't help but make the larger problem better. It certainly won't contribute to it getting worse.
That's for sure. I think you guys are, you know, doing a lot better in terms of most institutions, especially, I mean, you see the type of people that you're hiring, the kind of types of students that you're bringing in, so it's very refreshing to see that. And then everybody that I met today was really cool. We hardly talked about science, we were just like talking about life, like, it's really dope, so pleasure to be here. I hope I can come back some other time. You guys are awesome. And then definitely let me know, if you're in the Princeton area, feel free to hit me up, I would love to get in touch. And I still live in New York City, so if you're around over there, you want to watch a Yankee game, you want to watch the Yankees smack the Red Sox,
I will be there. Winner buys dinner.
You have to solve it. Okay, is that it? Because I'm getting tired.
Let's thank View one more time.